Hello, and welcome back to Training with Trisonius. I'm Trisonius. Today, we're going to focus on understanding the basics. So, these are going to be some basic building blocks. I do want to tell you it's not 100% required that you understand these basics in order to be able to program. However, there are some advanced programming concepts like bit shifting and bit manipulation that you will not be able to do if you don't understand these basics. I will admit that those concepts are used rarely in the grand scheme of things. So again, don't be frustrated or concerned if you don't fully understand the basics. It's not 100% required, but in order to be complete with this overall training, I did want to include it. So let's go ahead and get started. And so what we will learn. So we're going to learn about bits and bytes, which are some basic constructs and units of measures. We're going to learn about the different types of memory used in computers. Just like humans, computers have short-term and long-term memory. And so I'll be trying to explain it in those terms, equating it to human memory as much as possible in order to help you understand. Obviously, there are certain units of measure that we're going to discuss. Then we're going to talk about the metric system prefixes that are used to help us better understand the size of data and or the amount of units, the number of units that are being transported or used. And then finally, we'll get to the central processing unit or CPU. Okay, without further ado, let's go ahead and begin. So bits and bytes. Data is the key to all programming. In fact, every line of code, programming code that you write, is really designed to do one thing, and that is to manipulate data. So if the definition of a program is a series of computer-based instructions designed to manipulate data, then data becomes pretty important because all programming code is really designed to interact with, manipulate, or respond to data. Now, data can be categorized into two high-level types. Text, such as characters, strings, what you read in a book, so sentences, text, and numbers. Now, these numbers come in a wide array. So it might be that you're dealing with integers, which are whole numbers, or you might be dealing with fractional numbers. Even dates are derived from numbers. So two basic types at a high level of data, and that is text and numbers. So just keep that in mind. We'll refer back to this when we start getting into data types and custom types once we get to that point in the overall course. But I just wanted to introduce this concept that data is categorized into two high-level types. So data is represented in units known as a byte. So a single byte is comprised of 8 bits. And a byte can store up to 256 different values from 0 to 255. So keep in mind, 0 itself is a value. So a single byte can represent any one of 256 decimal values from 0 to 255. And a single byte is comprised of 8 bits. Now, bytes are filled with bits containing binary data, ones and zeros. So essentially, when we talk about the fundamental building blocks of data, it really is bits and bytes. And all you really have to understand is ones and zeros. Here, let's dive in a little bit more. I'll explain. So here, this long box represents a byte. Okay, 1 byte. And as we've discussed, bytes are divided into 8 bits. So let's go ahead and represent this by showing 8 individual boxes inside this byte. So there you go. There's 1 byte and it's comprised of 8 bits. Think of a bit as a small little bucket. So there we go, 8 small little buckets inside of a byte. You know what? Better yet, instead of talking about individual buckets, how about we think of them as switches? So what if there were a light switch inside of each one of these bits? That's probably more representative of the way we should think about this. So now each individual bit from right to left has a decimal value associated with it based on where that particular bit falls within the byte. So the bit on the far right has a decimal value of 1. Then if we go 1 bit to the left, it has a decimal value of 2. 1 bit to the left of that, a decimal value of 4. And you can see that each of the decimal values double as we move farther and farther to the left. And so it's the position of the bit within the byte that defines its numeric decimal value. Now, so each one of these bits, remember I said, was like a switch, and it has a numeric value associated with it. Now these switches, so inside the bit we can put a value, we can put a binary value, but binary values are only zeros and ones. So a 0 equals off and a 1 equals on. So if we were to put a 0 in each of these individual bits, we would have a binary value in each of the bits, but they would all be switches, right, that are turned off. So think of them as being turned off if it's a 0. Another way to think about it is a 0 is false and a 1 is true. So we could also state it like this. If we put a 0 binary value into a bit, it's flagged as false, meaning that if we were to ask the question, does this bit represent its decimal value, the answer would be false. No, it does not. But if we were to turn that to a 1, then it would be true. That would be like turning the switch on. And so if we put a 1 in a value, in one of the bits, a 1 binary value in one of these bits, then it would actually turn on that decimal value. Here, this is confusing, I know. Let's dig in a little deeper. So we're going to put zeros in each of the bits within this byte. So the binary value that we're looking at is 0, 0, 0, 0, 0, 0, 0, 0. So it's all zeros, right? There's 8 bits to a byte, so each one of these bits is turned off or has a value of false, right? Because they're all zeros. So the decimal value is 0. Now if we make a change, and let's turn the far right bit on, or set its binary value to true. What we've now told the computer is that this byte, since this far right bit is on, that far right bit has a decimal value of 1 associated with it. That means that that decimal value is true, meaning that if we looked at the entire binary value of 0, 0, 0, 0, 0, 0, 0, 1, the decimal value would be 1. Because the 1 bit, the bit containing the decimal value of 1, is turned on. Well, let's turn on another bit and see what happens. Oh, we turned on the bit that represents the decimal value of 4. So now our binary value is 0000 0101. Now this has a decimal value of 5 because the bit that has a decimal value of 1 is turned on, or it's set to true. And the bit that has a decimal value of 4 is also set to true. So what you do is you just simply add the decimal values together for each one of the bits that are set to true. In this case, we have the bit with a decimal value of 4 set to true, and the bit with the decimal value of 1 set to true. We add 4 and 1 together. So this particular binary value within this byte represents the decimal value of 5. Starting to make more sense? Here, let's try again. So let's add or turn on or set to true the bit with the decimal value of 32. So now our binary value is 001 00101. And this has a total decimal value of 37. So the 32 bit is turned on, the 4 bit is turned on, and the 1 bit is turned on. That means that 32 plus 4 plus 1, right? That's 37. So this byte has a total value of 37. Remember, I told you that a byte was comprised of 8 bits. And in one byte, you could represent any number from 0 to 255. Well, this is how it's done. So, what if we had a binary value of 0, 1, 1, 0, 0, 1, 0, 0? What would the decimal value associated with that byte be? I'll give you a moment. Okay, if you came up with a value of 100, you are absolutely correct. Because we would turn on the bit that represents 64, the bit that represents 32, right? And 64 and 32 is 96. And then we would also turn on the bit that represents 4. 96 plus 4, 100. I hope that makes sense. Okay, enough on bits and bytes. Let's move on. So remember I told you that there were different types of memory, and that I would do my best to equate a computer-based memory system to the way that humans think. So, just like humans, computers have what we're going to refer to as short-term and long-term memory. So, a human, they rely on their short-term memory to actually accomplish tasks. So whatever it is that they're focused on at that particular moment in time is what is loaded, if you will, into their short-term memory, or that becomes the focus of their short-term memory. Computers are no different. So computers, they also have to focus on completing a task, and the information or data that they're interacting with has to be loaded into their short-term memory so they can be part of their focus. So short-term memory in computer systems is also referred to as volatile memory. So let me give you an example of volatile memory, okay? So think back now. This isn't too hard. Think back. 4 days ago at 3:15 p.m., what exactly were you doing? Do you remember exactly what you were doing? More importantly, do you remember exactly what you were thinking? Chances are you do not, because your short-term memory is short-term, and 4 days is a little bit too long to be considered short-term memory. Now, you may have associated something with what was going on that day, and maybe you're able to recall exactly what you were thinking. But for the most part, I bet the majority of us cannot. Well, so our memory is volatile as well. What that means is that our short-term memory, after a while, gets cleared. It disappears, if you will. So for a computer, its short-term memory is volatile memory, meaning that it will clear after a period of time. A computer's short-term memory is referred to as RAM, or another way, RAM is short for random access memory. And yeah, random access memory is a type of volatile memory. So programs that are running on your computer get loaded into RAM so that they can execute. No different than, as you get ready to take on a task, you begin to look at something or pay attention to your surroundings, your eyes gather data, and that data gets loaded into your short-term memory so that you can begin to interact with it. It's very much the same thing. So programs, if you double-click on a program on your on your computer, it loads it into short-term memory so that it can execute. Now, data must be loaded into short-term memory or RAM before it can be used. Well, it's the same with us humans, right? If we're going to focus on something, we need to do just that. We need to focus on it, get our mind wrapped around it, get our mind in the right place, and then we can begin to attack it from a systematic perspective, mentally, using our short-term memory. The same thing's true from a computer perspective, and that is that applications and data have to be loaded into its short-term memory, or RAM, before it can be used. Now, data, this is important, data from short-term memory can be written to long-term memory. We'll get to long-term memory in a moment, but this would be equivalent to, you experience something in your life, it's currently in your short-term memory, you don't want to forget it, so you pull out a diary and you begin to record, or a journal, and you begin to record on paper using a pen exactly what it is that you experienced, what you were thinking at that point in time, so that you can capture that information. And the reason that you use journals is because your short-term memory is not reliable. Once you go to sleep at night, wake back up, you may not remember everything completely. And so you want the ability to load those memories back from a long-term device, in this case, your journal, so that you can remember what you were thinking at that point in time. Now, the computer is the same way. It can load information from long-term memory into its short-term memory to be executed. Now, when a program ends, or the computer's turned off. So let's say we loaded Microsoft Word up. When we double-click on the Microsoft Word icon on our desktop, it actually loads the Microsoft Word program into memory and then paints stuff on the screen for us. And the processor, the computer processor, which we'll get to in a minute, begins to execute instructions that are part of the Microsoft Word programming code. Now, when we close Word, what happens is that program and the data gets cleared from short-term memory. Another way of saying it is that the RAM, or random access memory, is purged. That memory is freed up to be used by another application. So unless we saved our work to long-term memory, our work is gone. So speaking of long-term memory is referred to oftentimes as non-volatile memory. Because see, if your computer gets turned off, your power goes out, or you close a program, whatever it is that you were working on could have been saved to your hard drive. So a hard drive or a solid-state drive are types of non-volatile memory. So data can be stored in non-volatile memory. And this memory is not cleared or erased when a program ends or the computer is turned off. Now, it doesn't mean you can't clear it from non-volatile memory. You certainly can do so, but typically that needs to be done on purpose. The computer isn't just going to forget that information. unless there's a defect of some kind that occurs within the computer system. Anyway, non-volatile memory is used for long-term storage. So data from long-term memory can be loaded into short-term memory for usage. Going back to our Microsoft Word example, let's say that you were working on a paper for work or you were working on a paper for school. You typed up half your paper, you saved it to a location on your hard drive. When you save it to your hard drive, you're taking it from short-term memory and you are putting it into long-term memory. Now you can close the application. Later on, when you're ready to work on it again, you come back, you double-click the Word icon, it opens Word back up, and then you're able to load whatever it is that you were doing from long-term memory back into short-term memory so you can begin to work on it again. I hope that makes sense. I'm not trying to oversimplify this too much, but I am trying to equate it to the way that we as humans think, just because it gives us a point of reference from which we can begin to communicate and understand. Okay, moving on. Units of measure. There are three most common units. Units of measure that are most commonly associated with computer science. We've talked about two of them. One of them is a bit. So a bit is a unit of measure representing 1/8 of a byte. Or another way of saying this is a bit holds a single binary value, which is a 0 or a 1, and it represents 1/8 of a byte. Now, a bit is referenced with a lowercase b. A byte is a unit comprised of 8 bits holding a decimal value ranging from 0 to 255. We talked about that already. And a byte is referenced with an uppercase b. So anytime that you see lowercase b, it's bits. Anytime you see an uppercase b, it's bytes. And we'll get to that in a second. It'll make more sense. Now, we haven't talked about this one yet, hertz. Hertz is referenced with the letters HZ. So a bit and a byte represent physical storage or physical size, whereas hertz really represents what's known as a cycle. It's the number of, a hertz is one cycle in 1 second. And it typically represents a single cycle in which a single instruction can be executed. I'll explain this in a little bit more detail in a second. But just realize that 1 hertz is 1 cycle. So computer systems of today deal with large amounts of these 3 unit types. So you might have heard about a 64-bit machine or 64-bit processor on a computer that is 2.4 gigahertz processing speed with a hard drive of 1 terabyte of storage capacity. And so even just talking about that, you can see where bits, bytes, and hertz come in, right, into the overall picture. Anyway, because we're dealing with such large numbers in computer systems, there's a shorthand based on metrics prefixes that help us define these numbers in a more specific and scientific manner. So these metric system prefixes, you've heard them, kilo, mega, giga, and tera are among a list of the prefixes used to denote the quantity of something, such as a byte or a bit in computing and telecommunications. So let's go back to that for a second. Well, let's get to the next point. Sometimes called prefix multipliers, these prefixes are also used in electronics and physics. So each multiplier consists of a 1-letter abbreviation and the prefix it stands for. So kilo, right? Kilo represents thousands, but it's represented with a capital K. So you may have 15 KB, with the B being a capital letter B. What that would mean is 15 kilobytes, KB. Kilo is thousand, so we know that would be 15,000 bytes. And we know a byte has 8 bits. So already you're beginning to understand this if you didn't know it already. So 15 KB. There could be 15 MB, right? Megabytes, which would be 15 million bytes. And then giga and tera. So if we dig into this a little bit more, you can begin to see that a bit, obviously that's one bit. An example of that would be 1B, lowercase b. Then you have your byte. That's equivalent to 8 bits, and it would be 1 capital B. Then you have your kilobyte. A kilobyte is 1,024 bytes. So everything is done in increments of 1,024. So, because again, it's metric based, it's not 100% decimal based. So, and it's an 8-bit system. It's a base 8 numeric system that we're working with. So everything has to be divisible by 8. Anyway, 1,024 bytes is 1 kilobyte or 1 KB. 1,024 kilobytes is 1 megabyte or 1 MB. 1,024 megabytes is 1 gigabyte or 1 GB. And so on and so on. I hope that makes sense. All right, let's go ahead and jump down to the central processing unit. I'll just give you a real high level. We talked about this already, but the central processing unit, or CPU, is considered the brain of the computer. But keep in mind that memory, random access memory, so short-term memory and long-term memory are actually separate. They're not part of the CPU. So you could add more memory to your computer without changing your CPU. And you could add, more hard drive space, which would be long-term memory, without changing your CPU. So they are totally separate. They're modular. They're segmented and separated from one another. So when we say that the CPU is considered the brain, think of the brain as your cognitive reasoning capability without memory. Now, the CPU is responsible for retrieving instructions from random access memory and processing them. So the CPU, this brain, cognitive reasoning capability, or of the computer, the brain of the computer, reaches out to the short-term memory, grabs information from the short-term memory, and executes it. So it can execute a certain amount of information or a certain amount of data or set of instructions per second. So a 64-bit processor can execute up to 64 bits of information, right, per cycle. And that's actually, that's right, 64 bits per cycle. A 2 gigahertz processor can process 2 billion, it basically can process 2 billion instructions per second. Remember hertz? 1 hertz is 1 cycle per second. So 2 gigahertz is 2 billion cycles per second. So in each cycle, we can execute up to 64 bits of information. So that's a lot. That's a lot of information to be able to process. So a quad-core processor is equivalent to 4 processors running in tandem. So a 2 gigahertz quad-core processor means that you have 2 gigahertz processors running together, which could process up to 8 billion instructions, each one being up to 64 bits in size per second that it can read from random access memory. I hope this makes sense. I hope it helps some. If not, there's a lot of information on YouTube, and you can pose questions in the comment section of this video, and I'll do my best to answer them for you. Okay. So, in review, we've learned that a byte is a unit of measure containing 8 binary bit values holding up to 256 different decimal values, ranging from 0 to 255. Wow, we did learn that. And we know that bits contain binary values consisting of ones and zeros, indicating that that bit is either true or false, right? On or off. The placement of a bit within a byte signifies its decimal value, but the bit must contain a binary value of true to have a corresponding decimal value. In other words, if you have a byte, you have 8 bits. We know that the bit on the far left has a decimal value worth 128, and the bit on the far right has a decimal value worth 1. But you must have that bit turned on, or have it must contain a value of true, a 1, in order for that decimal value to be counted. So we also know that all programs are executed from short-term memory, or random access memory is the more appropriate term. Just like humans, we have to focus on what we're doing, so does the computer, so it needs to load it into RAM, the program and the associated data. Short-term memory is volatile, so writing data to long-term memory devices, such as a hard drive, will allow the computer to load the data back into short-term memory for execution at a later date. Remember our conversation regarding the Word document that we saved and then came back and opened later? Metric prefixes are used to represent larger numbers, such as mega for million and giga for billion. We talked about that. And then finally, we learned that a computer processor speed is measured in units known as hertz, and 1 hertz is equivalent to 1 cycle per second. So when we have 2 gigahertz, then that's equivalent to 2 billion cycles per second. Awesome. We learned quite a bit. Again, it's not 100% necessary that you understand all of this to be able to program. But once we get into some of the more advanced features, you will want to know this information. So I do encourage you to continue to study on what we've talked about. If there's anything that, again, that you don't understand, post a question below the video in YouTube, and I'll be happy to answer it. Or take any of these concepts that I've discussed and go to Google and do a search on them. So, in order to help reinforce what we've learned, I've got a short assignment for you. So I want you to randomly create 4 binary values representing a single byte and calculate the decimal value associated with each. You know, just randomly put down 0, 1, 1, 1, 0, 1, 0, 1, whatever, you know, and then figure out what the decimal values are. 4 binary values, 4 bytes. And then we reviewed a single byte. But do you know, and we didn't go into this, but you can combine more than 1 byte to store larger values? I'm sure you kind of asked yourself this question already, because since a 1 byte can only store a value up to 255, I'm sure you've thought, you know, wow, computer systems can store numbers that are in the millions and billions. So how's that done? Well, what you do is you combine multiple bytes together. So, in the example that we have here, 2 bytes can be combined to represent a decimal value up to 65,535. So if you combine 2 bytes together and you turn on or set the bit flag to true for every single bit in the 2 byte value, it would equal a decimal value of 65,535. Can you figure out the decimal values for each of the bits in the image below? The first 3 values are provided for you in red. Go ahead and figure the rest of it out. So this is your assignment. And again, I appreciate you taking the time to watch this video, and I hope you learned a lot. And we'll be digging into some actual programming code in our next lesson. Until then, have a great time learning and programming. And this is Trisonius signing off.